So the title of these lectures was and is Supergravity at Work. So today we will have the first example of supergravity at work, meaning that I will try and take what I taught you so far and show you some simple models, some simple setups from which we can have some understanding of what happens to physics when you deal with supergravity theories. Then the plan, if everything goes right with the time, is tomorrow to finish the discussion of today. Now we'll see how much I'm able to do today. Do a brief introduction of n equals 2 supergravity, so an extended theory of supergravity, because then I will show you in the last part, again, supergravity at work, looking at supersymmetric solutions of supergravity, especially of n equals 2 supergravity, and in particular of black holes in n equals 2 supergravity, so that we can also make a connection between what you have seen in the course by Monica with what happens in supergravity, okay, when supersymmetry is present. So let me start first with a more formal point, which, however, has also some peculiar, I would say, physical consequence. And this is the fact that I already discussed a number of times, the fact that the scalar manifold parameterized by the chiral multiplets in supersymmetric theories is a Scalar manifold, whereas in supergravity theories, it's a Hodge-Scalar manifold. So the difference is essentially the following, that on this manifold, when you take two open sets of the manifold which are overlapping, you will define, of course, you will have coordinates which might change as well. No, you might have that the coordinates are, of course, parameterized by your chiral fields, but this also can be reparameterized. No, you can change the way you parameterize your coordinates on the manifold, and therefore you can parameterize with a certain set of coordinates one patch of the manifold, another set the other patch of the manifold, and you have to explain how to move from one to the other patch. But also, since on a Scalar manifold you have a structure which is given by the Scalar potential, you will have to have that the Scalar potential in the two patches is related by a Scalar transformation, which is essentially shifting the Scalar potential by the real part of a holomorphic function. Okay, there was a question from home? Okay. So this is holomorphic, whereas K, of course, is real, as we already discussed. Okay, and we'll see later an example in particular. Now, in global supersymmetry, in rigid supersymmetry, the Scalar potential never appears explicitly in your action, nor in the supersymmetry transformation rules. What happens is the metric, this space is a metric space. On this manifold, you also introduce a metric, and the metric depends on the Scalar potential by means of the second mixed derivatives. And this is the quantity that appears in your Lagrangian, and therefore this ambiguity is nowhere to be seen in your rigid theory. However, when you go to supergravity, we have seen that there are places where the Scalar potential appears naked, and not only that, we have seen that the gravitino, the supersymmetry parameter, the Gaugini transform. So if you had to do the same thing, and now also for the fermions, you will have to define all these fields on the patch A. This will be related to the same fields on the patch B. So gravitino, Gaugino, etc. By the exponential by a rotation, a chiral rotation. Now there's a gamma 5, and there's the imaginary part of the Kähler transformation there. And let me put here also the chiralini. Of course, there is a sign here which is plus or minus depending on the fields. Now we discussed that you have a certain sign for the gravitini, the supersymmetry parameter, the Gaugini, and you have the opposite sign for the chiralini. The important thing, though, is that when you go from patch A to patch B, the spinors have to rotate. Moreover, the superpotential has to transform by means of the same holomorphic transformation that enters in the Kähler potential. So what is this telling you? This is telling you that the manifold has an additional structure, has a complex line bundle, complex because you see here I have a complex section which is given by the superpotential which transforms with this holomorphic function h, and then you have a principal bundle embedded in there which is the U1 essentially rotating the fermions. And this is now important because of course in order for this thing to be consistent you need to have the usual requirements that, for instance, if you have 3 patches now, the transition functions that allow you to go from A to B, then from B to C, and then from C to A should close. Okay? And this is in general a non-trivial consistency requirement. Now, on the Kähler manifold, you have a Kähler form, which I said is defined in this way. And because of the fact that, again, the metric is the second mixed derivative of the Kähler potential, and the connection which introduce the U1 connection for this transformations, let me get the right sign. The connection that you introduce is also related to the derivatives of the Kähler potential. This tells you that in the supergravity, in the local case, this Kähler form is actually the field strength of this connection. And this is now the interesting thing, because this is what imposes the constraints that I was telling you, that appear in supergravity and are not there in global supersymmetry. Because now, this being a field strength of a U1 will satisfy generically quantization rules whenever you have closed cycles on your manifold. So if the scalar manifold is trivial, let's take that you, for instance, a chiral multiplet with a canonical kinetic term, phi bar, for the Kähler potential, then nothing happens. The same thing is true, is valid, the same Kähler potential is valid for in global supersymmetry or in supergravity. Because your moduli space, your scalar manifold is just C, there's nothing there. However, take a very simple example that is the case where I now take as a scalar manifold the sphere. So I still have one complex scalar field. I take a 2-sphere. Then the 2-sphere, of course, is itself a 2-cycle.
Sorry.
And yeah.
We can see the blackboard anymore.
Yeah, we have some technical problems. You should be able to see it soon.
Okay, I'll wait for a second and then let me know when you see it.
Okay, thank you.
Okay? Do you see it? Do you see the blackboard or not at home?
Yes.
Yes,
Okay.
now, yes.
Okay, very good, thanks. By the way, can I erase now this one up here or it can, okay, just to know. Okay, very good. You all took note. Okay, you know where to go tonight. So let's take now as a scalar manifold, rather than simply flat space, flat Euclidean space, complex, of course, because we need chiral multiplets, but let's take a sphere. So the complex projective line. And on the sphere, you can introduce coordinates. You can introduce coordinates in the usual way. So you can, well, there are several ways to introduce coordinates on the sphere, of course. But you can use a stereographic projection, meaning that you take your sphere, Giotto at work here. Yeah, a nice egg. Anyway, so you have your sphere, and for instance, you project starting from the North Pole on the plane. So you will have that a point that is on the upper half of the sphere, like this one, will end up projected someplace outside the circle, and points which are instead in the lower hemisphere are going to be projected somewhere inside, okay? So that essentially, you see, you associate a point, a phi field, which is a complex number, for each of the points of the sphere, except, of course, for the North Pole, which would be projected at infinity. Okay, of course, you have to remove one point in order to cover the sphere. You cannot cover the sphere with a global, with global coordinates, the two sphere, at least. And hence, you need to introduce projections. So you can introduce a projection from the North Pole, like this one, or you could introduce projections from the South Pole. So let's call z the coordinate that starts from the South Pole. So I have z at infinity here. And then the projections, of course, will be different, even though, again, well, the same point here now would be somewhere inside the circle, and the point that was here would go somewhere outside, no? So whether you use phi or z, well, you see right away that the change of coordinates is simply that z is 1 over phi, no? Whether you project from the North or from the South Pole. You can still project essentially on the plane the points of the sphere, but of course, in order to cover the full sphere, you need at least 2 patches, okay? You will have one patch that covers the whole sphere except for the North Pole, and you will have another patch that covers the whole sphere except for the South Pole. So now, in what is the metric that you can write down for such a manifold? Well, the Kähler potential that you can introduce is essentially a certain number here, which you can put to be whatever you like. And I'm using now, well, okay, I'll introduce now normalizations again later, but let's assume for now that these phi's are adimensional rather than with a certain dimension. And the point is that from this Kähler potential, of course, you can introduce the metric. Well, it's a one-dimensional metric, of course. It's just g phi phi bar. And from the second derivatives, you will end up having this number n, which remains there, and then you have the second derivative. So you first take derivative of the log, then the derivative of the whatever you get, and you end up with something like that. Okay, so this is your metric, which is the metric of the sphere in stereographic projection. The point is that at this level, for this moduli space, as long as I am in global supersymmetry, n can be an arbitrary real number. Okay, it's just related, if you wish, to the well, it's a coefficient that appears in your metric, so this could be related, if you wish, again, yeah, to the radius of the sphere, but it's completely arbitrary at this stage. the fact that you can change coordinates will tell you that when you go from the patch where your Kähler potential is described in terms of the coordinates phi to the patch where you describe the same space with the coordinate z, is related by a Kähler transformation. No, in fact, this is what this is the K. Okay, let me call this, I don't know, Ka, just to do the same thing as I did there. So Ka is going to be like that. Now, if I rewrite this in terms of the z coordinates, of course, I have to do a change of coordinates. So I will have to express phi in terms of z, or z in terms of phi. So if I write Ka minus Kb, meaning that Ka is the one expressed in terms of phi, and Kb is the one expressed in terms of z, and which, of course, will be exactly the same, the difference is going to be essentially this number times the ratio of the logarithms, of course. No? You will have 1 plus phi star divided by 1 plus z star. Okay? Now, of course, since the two coordinates are related, I can rewrite both in terms of the coordinate phi, for instance. And then you see right away what happens. What happens is that here I get the same, if I multiply by phi star, I get phi star again plus 1, which goes away with that, and then I'm left just with the phi star that I have here. But log of phi star is n log of phi plus n log of phi star. So this is my transition function, which is holomorphic. Okay? Now, you see, well, if you introduce dimensions, since then I want, at some point, I will introduce back the mass dimensions, then the Kähler potential should have mass dimension 2, so I should put some Planck mass squared here as well, which means I will have some Planck mass squared there as well, which means that also here I will have a Planck mass squared everywhere. Well, let me do like that, actually. Let me write this divided by mp squared is whatever it is. Now, why am I doing that? Because then, you see, when I do the chiral rotations, the rotations are given in terms of the exponential of 1 over 4 mp squared h minus h bar on the fermions, and then you have a gamma 5, of course. Let's take either the left or the right-handed fermion, no? So I will have a plus or a minus. It's not too important the sign now. I don't care about the sign. What I care, though, is the fact that now, when I'm taking, for instance, a fermion living on the when I'm covering the manifold, no, and of course I have that, for instance, this circle is covered by both patches. When I go from one patch to the other, I have to change, no, as I said, the fermions with a rotation. And now, if I do this in terms, using these transition functions, you see that this becomes the exponential of n over 4, the log of phi over phi star. Okay? So if you take phi and you parameterize phi in radius and the phase, okay, norm and phase, the norm here clearly goes away, and you're left with the exponential of n over 4, and then you have, well, yeah, the log of the exponential of 2I alpha. Let me call alpha the phase. No? If I say that phi is norm and phase, then I get something like that. Why is this interesting now? Because, of course, this means that in terms of alpha, essentially you end up having a rotation which is n over 2 now, I alpha. Okay? And alpha is essentially the angle parameterizing the equator, no? Because in this, you see the fixed point is when you have a radius 1, and then alpha is the angle around here. And so clearly, you would like your functions to be well defined once you do a tour around the equator. So you would like not to pick up a phase when alpha goes into alpha plus 2 pi. No? This is a circle in the equator. You will have whatever it is, your function, your field that has to transform from one patch to the other. When you send alpha in alpha plus 2 pi, you better find the same expression. Though now you see that when you send alpha in alpha plus 2 pi, you get an extra factor here. You pick up an exponential of ni pi, which unless n is even, gives you a sign, gives you an extra sign. So this tells you that if you don't want to pick up an extra sign, n now in supergravity cannot be a real number. So this is global. Whereas in supergravity, n should be an even integer. And now the fact that it is an even integer gives you some interesting constraints. Well, first of all, it tells you that while in global supersymmetry you can pick up a Kähler potential which has an arbitrary coefficient here, not all these manifolds that you have in global supersymmetries can be coupled consistently to gravity. Only those where n is an even integer. So if for some reason you have phenomenological features that requires then n to be, I don't know, root of 3, then this you're not going to be able to reproduce in supergravity. So this is a restriction, not a very big restriction, clearly, also because it appears, because our manifold is a special manifold here that has a 2-cycle because it's a sphere. If you were on the flat space, you wouldn't see this kind of restriction. So it depends on the fact that you have 2 cycles. And essentially, it has to do, if you wish, with the fact that the flux of J should be quantized, okay? That's related to this fact. This is a field strength now, and if you have a sphere on which you can look at the flux of this 2 form, then this has to be quantized, and that's what you see here. But the other interesting thing, which is a curiosity that was noticed by Witten, which however is interesting to point out because, again, it shows that this could have, in principle, a physical impact, is the fact that from this, you could also imply in supergravity that Newton's constant has to be quantized. Because if you take the supergravity action and let me look now only at the relevant part, which is gravity plus the scalar field manifold here, then we said for this particular manifold, this is n m Planck. Yeah, well, now this is if I use the one without dimensions, actually. Here is if I use the dimensionless one, but anyway. This is the coupling you get there. And we said that now n has to be quantized. And the thing is that you interpret generically, when you have a sigma model, no, when you have a generic sigma model of field, I don't know, the sigma model for pions, no, or whatever it is now, for certain fields, pi j, the coefficients you have, oh, let's take just one for simplicity now. The coefficient you have in front is the, sorry, you have generically a dimension-full coupling constant in front, which is the coupling that tells you the strength of the self-interactions of your pion. No? Here you have some functions of the pion, which might be more or less complicated. In our case, you see, it's not very complicated. And this coupling constant is what tells you what is the strength, essentially, of these self-interactions. And if this is a sigma model, which comes from some maybe strongly interacting theory, I don't know, whatever it is, this quantity is generically quantized, okay? And now you see our F square for this particular model is the Planck mass squared times n. So you see, this tells you on the other way, you can interpret this in the other way, or you can interpret this as the fact that the Planck mass is, or if you wish, since there is a relation between the Planck mass and the Newton's constant, so this is 8 pi gn, this tells you that g Newton is quantized in terms of f, because n now has to be an even integer. So somehow the Newton's constant comes out constrained again in supergravity, well, in this particular model, because of the quantization that you have, sorry, on the coefficient in front of the Kähler potential, because of the fact that the manifold is not simply Kähler, but it is Hodge-Kähler. Because of the fact that you have that the superpotential transforms the transformations as well as the fermions. And in order to have all the fields well defined on the manifold, so that, as I said before, when you have different patches, you can cover globally the manifold in a consistent way, consistency forces you to have quantization conditions like this one every time you have essentially 2 cycles. Okay? So it's not a big deal. As I said, it's not a very strong constraint. It applies when you have 2 cycles. Most of the cases that, most of the times you're interested in very simple Kähler potentials, you don't have complicated manifolds, you don't have 2 cycles. Also the moduli spaces that you usually not, well, you use local versions generically, so not compact, you don't look at the global properties. So most of the times you don't see this problem even when you do phenomenological models in supersymmetry or in supergravity. But the message is that you have to be careful to go from global supersymmetry to supergravity, because the nature and the properties of the scalar manifolds are going to change. Okay, that's the main message, beside all the details that we have here. And as I already mentioned, this becomes even more apparent and more strong when you go to extended supergravity theories. So while in global supersymmetries you have Kähler manifolds, and when you do extended in 4 dimensions, of course, and when you do extended supersymmetries, you still have Kähler manifolds, only of restricted type. In supergravity, that's not the case. When you enhance the number of supersymmetries, the nature of the scalar manifold changes, which means that the couplings between the scalars change in a way that an n equals 2 theory cannot be written down as a special n equals 1. An n equals 3 theory cannot be written down as a special n equals 1. N equals 4 is also different from n equals 3, 2, 1, and so on and so forth. So each supergravity theory is different from any other supergravity theory with a different number of supersymmetries. So while when you study supersymmetry, You can learn n equals 1 supersymmetry in 4 dimensions, and then everything else is just a restricted theory, a restricted n equals 1, because you have additional supersymmetries maybe, but it's just a special case of n equals 1. In supergravity, it's not enough, unfortunately, to learn n equals 1 supergravity. Because if you have to deal with n equals 2 supergravity, the theory is different. It cannot be written down as an n equals 1. The couplings are different. The type of interactions that you get are different, and therefore you have to study it by itself. And this is the reason why you find so many papers about n equals something supergravity in a given number of dimensions, because each theory in a different number of dimensions is different from another. Okay, any questions so far? Yes. 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 That's exactly, from the mathematical point of view, that's exactly the definition. Yes.
Can you clarify a little bit this last statement? If you have an extended supergravity theory, it is not invariant under n equal 1 supersymmetry?
I will show you n equals 2. I will discuss this when we get there, okay? Remind me again, I will explain this when we get to n equals 2. Of course, you will always have, if you have two supersymmetries, it must be separately invariant with respect to each. But as I said, the couplings are going to change. And you cannot write down, well, it has to do again with the gravitinos, essentially. You cannot write down an n equals 2 theory as an n equals 1 supergravity coupled to a gravitino multiplet, because the second gravitino multiplet should be a massless multiplet, and the interactions that appear cannot be written down in a simple way n equals 1. I mean, you don't know how to couple n equals 1 to a massless. I mean, the way you couple an n equals 1 to a massless gravitino multiplet is n equals 2, and this creates a whole sorts of different additional structure. But I will come back to this later. Precisely because the chiral multiplets, for instance, you have in n equals 1, you can combine two chiral multiplets and obtain a hypermultiplet in n equals 2. But when you do it in supergravity, the scalar manifold parameterized by the hypermultiplet is not Kähler. There are restrictions which makes it non-Kähler. Okay, well, but we'll discuss it briefly tomorrow. And in any case, we can. I'll be here anyway all morning. I know we skipped the lecture tomorrow morning, but I mean, at some point, if you are interested, we can discuss more. So let's look at some features, physical features of supergravity. Let me start from the scalar potential, which, as I mentioned, is the sum of the F term part so this is the improvement of the F term of global supersymmetry. Instead of having simple derivatives of the superpotential square, you now have covariant derivatives, and you need the exponential of the Kähler potential in front in order to make it covariant. Then there is a contribution that appears only in supergravity, and in fact, it is Max-Planck suppressed. And then you have the D term. So here you get the gauge kinetic functions, the inverse of the gauge kinetic functions, and these are the prepotentials of the isometries that you gauged. You remember that there is a relation between the prepotentials and the Killing vectors on a scalar manifold, and so this is the structure of the scalar potential. This is the D term part, this is the F term part, and this is the new, I don't know if I want to put it in the F term or not, it's the new contribution coming from gravity. And you can see that if you look at the supersymmetry transformations, the gravitino has a supersymmetry transformation of this form, the plus, of course, whatever else, but this is the part that interests me. The Gagini, the chiralini have an expression of this type. And again, plus anything else. I'm not interested in the rest. I'm looking at the parts that are relevant for the discussion that I will do in a moment. And the Gagini have di, which is a structure like this, and again times epsilon. Now, why am I interested in looking at that? Because as I already mentioned several times, no, when we discussed, for instance, the cosmological constant, I told you that the potential is something of order g square that comes from the square, the order g changes that you do in the supersymmetry transformations of the fermions. And in fact, you see that this thing here, if you square it, gives the first contribution. So you can, well, with some coefficients, but this is essentially the square of the shift of the chiralini. This is the square of the shift of the gravitini. And this is the square of the shift of the Gagini. Okay? And the important thing here is that matter fermions will always contribute with a plus sign, the gravitinos will contribute with a minus sign. So this, of course, is consistent with what you have from global supersymmetry. In rigid supersymmetry, of course, mass Planck goes to infinity, so this disappears, the gravitino disappears. You still have these two contributions. This goes to 1. Here you just get the derivative of the superpotential, and then you get two positive contributions, the derivative of the superpotential square, the d terms squared. When you have gravity, you have a negative contribution. And this is crucial now, because this tells you that while in global supersymmetry, the supersymmetry breaking scale and the cosmological constant are related, in supergravity, this is not the case. So you see, if I'm interested now in a vacuum, in a maximally symmetric vacuum of my theory, I set to 0 all the fields, except for the metric, if I am in a gravity theory, of course, because I might have a cosmological constant. And I want to keep the scalars as constants, no? So what do? I have a potential there. This potential depends on certain scalars. I can take the condition that minimizes the potential. This fixes for me the value of the scalar fields to certain specific numbers. I don't know how to call it. Let's put a hat on top of the phi. So this is a number now. So it does not depend on x. It's constant. And then if this is constant, V becomes just a constant. It's a cosmological constant, effectively, which can be either positive, negative, or 0. And I can have critical points of all types. Okay, my scalar potential could be like this, for instance. And then here I have a positive cosmological constant. Here I have a negative cosmological constant. Here I have a 0 cosmological constant. And this has nothing to do with breaking of supersymmetry per se. Because you see, the breaking of supersymmetry is related to the fact that now you look at the supersymmetry transformation rules and you check whether on these backgrounds, so once you fix the scalars to these values, whether the supersymmetry transformations here are 0 or not. If all three are 0, then you are on a supersymmetric vacuum. If they are not 0, you break supersymmetry. Okay? So I'm setting all the fields to 0, so there is nothing here essentially that remains. The scalars are constant, so also the derivatives of the scalar disappear in my supersymmetry transformation. Then the only remaining pieces in the supersymmetry transformations are precisely these three contributions, which are the ones that enter in the potential. Now the scalars are just constants, so these are just numbers, essentially. And I have to check whether this is 0 or not. And then you see, having supersymmetry requires, essentially, that the covariant derivative of W gives 0. The analogous of the case in global supersymmetry that the derivative of the superpotential should be vanishing to have a supersymmetric vacuum. The D terms have to vanish. Of course, all this is for this particular value, so on the critical point, okay, at the critical point. And the supersymmetry parameter, this becomes a differential equation. You see, the Gravitino condition becomes a differential equation. It tells you that the covariant derivative of the supersymmetry parameter should be proportional to a certain constant times gamma mu times epsilon. Okay, so this is a differential equation. And this will depend on whether you are in ADS or De Sitter or Minkowski. Okay? Now, these are the conditions in order to have supersymmetry, but let's say, I mean, this is a differential equation that essentially tells you how to write down epsilon once you are in a certain vacuum. And therefore, the supersymmetry conditions are essentially these two conditions here. If the derivative of W is different from 0, or the prepotentials are non-vanishing, then you have SUSY breaking. So the scale of SUSY breaking is going to be related precisely to the non-vanishing of the derivative of the superpotential or of the prepotential. Okay? And so let's say lambda SUSY to the fourth, for instance, is related to dW square or to P square. And from what we said, moreover, P and dW are related, no? If you remember. So there are also relations between the two, so that generically when you have one turned on, also the other is turned on. And if they are both vanishing, then you don't have supersymmetry breaking, and everything is fine. But now you see, if I have supersymmetry, and these two are 0, then there is one thing that I can say for sure. The potential at the critical point, if I want to preserve supersymmetry, will have the first term, which is vanishing, the last term, which is vanishing, and therefore it must be negative or 0. So you want to preserve supersymmetry, the cosmological constant has to be either vanishing or 0, which again goes well with what we learned, that De Sitter breaks supersymmetry. The vacuum cannot have positive energy. If you want to preserve supersymmetry, the vacuum energy either is 0 or it's negative. The difference, though, with respect to global supersymmetry is that it can be negative. You can have a negative cosmological constant, as we learned. You can have anti-De Sitter supergravity and preserve supersymmetry. Now, in global supersymmetry, you had that SUSY would imply V equals 0, and V non-zero would imply supersymmetry breaking. Now, here, SUSY implies that V has to be negative or 0, and therefore, clearly, if you get a positive cosmological constant, then you're sure that you will have that SUSY is broken. But now, this is not an if and only if. That's the interesting thing. Because you see, I could have supersymmetry breaking, I could have dW non-zero. Let's say that I don't have a gauging, so I just have dW and W, so I have only the first line here. I could have dW different from 0, so I could have supersymmetry breaking and still have a cosmological constant which is 0, if the superpotential is non-vanishing. So supersymmetry breaking can appear for positive cosmological constant, for negative cosmological constant, or for 0 cosmological constant. Depends on the value of W. If dW is non-zero and W is different from 0 in such a way that these two terms cancel, then I have supersymmetry breaking in Minkowski. If W is bigger than dW, then I have supersymmetry breaking in anti-de Sitter. So while, you see, so the situation is very different from global supersymmetry. In global supersymmetry, you know that supersymmetry means 0 cosmological constant, and 0 cosmological constant means supersymmetry. Supersymmetry breaking, positive cosmological constant means supersymmetry breaking. It's an if and only if. Here, supersymmetry tells you that the cosmological constant has to be either 0 or negative, but you can have 0 or negative cosmological constant and break supersymmetry. So you understand that it's crucial, if you want to analyze supersymmetry breaking scenarios and you want to analyze the properties of the vacuum, and in particular the cosmological constant, you better do it in supergravity rather than in field theory. Neglecting gravity is a very big mistake if you're interested in the value of the cosmological constant, because your mechanisms of supersymmetry breaking may allow you to have a very large scale of supersymmetry breaking and still have a small cosmological constant, because the cosmological constant, which is related to the potential, is essentially the scale of supersymmetry breaking minus that term, which is essentially related to the mass of the gravitino. Why? Because if you remember, in the Lagrangian, the Rarita-Schwinger part, we had the kinetic term, and then there was precisely this term, of course, plus remission conjugate, so that this thing here is the mass, the Lagrangian mass at least. Then we'll discuss whether this is the real meaning of mass or not. That depends on whether you are in Minkowski or in anti-de Sitter. But the Lagrangian mass for the gravitino, since now we are on a vacuum, so this is just a number, the Lagrangian mass of the gravitino is precisely the contribution you get there. Okay? Well, some terms related to the Planck mass as well, really. This is really, yeah, I've been a bit imprecise here because that is W divided by Planck square, so this is really the mass. It's an average of the mass of the gravitino and the Planck mass, no? Anyway, the important thing is that the value of the cosmological constant is not directly related to the scale of supersymmetry breaking. You can have a huge scale of supersymmetry breaking and still have a small cosmological constant. The two are, they are related, again, because of the form of the potential, but they're not directly, there is not a linear dependence. I mean, it's not like in a direct linear dependence like in supersymmetry. Okay. So actually, it's interesting to notice that if you look at Minkowski, supersymmetry breaking in Minkowski, or small cosmological constant for that matter, if you have a small cosmological constant, like the one that we have today, for instance, which essentially you cannot distinguish from zero, then the scale of supersymmetry breaking and the mass of the gravitino are related. And actually, you can work out the precise relation from the formula above. Somebody at home? It was just an interference, I assume. So the mass of the gravitino comes out related to the scale of supersymmetry breaking square divided by the Planck mass with a factor of √3 because there is that 3 factor there. The factor of √3 is a detail that depends on the particular dimension in which we are. But this is the thing, no? So in Minkowski, this is an exact relation. Of course, if you are in de Sitter, for instance, with a small cosmological constant, this is an approximate relation. But of course, if you assume that the scale of supersymmetry breaking is large enough, for sure beyond the TV, then this number is also generically much larger than the cosmological constant that we see today. So that is a good approximation. So when you go from supersymmetry to supergravity, the scale of the cosmological constant and that of supersymmetry breaking now, they can be tuned separately, essentially, depending on the model. Then you can ask the question, what happens if I want to take the rigid limit? Because if I have a supergravity theory and I send the Planck mass to infinity, I should be able to obtain back a supersymmetric theory. Well, not quite. And here you start seeing the differences, no? And why this is related to what I'm saying here. Because you can actually consider two different rigid limits, depending on whether you want to keep the mass of the gravitino fixed, or you want to keep the scale of supersymmetry breaking fixed. Because you see, if you keep the mass of the gravitino fixed, since the scale of supersymmetry breaking is related from that relation to the mass of the gravitino times the Planck mass, if the mass of the gravitino is fixed, then in this limit, when m Planck goes to infinity, also the scale of supersymmetry breaking goes to infinity. And then, if the scale of supersymmetry breaking goes to infinity, this means that essentially you're living in a phase when supersymmetry is broken all the way. Now, if the scale of supersymmetry breaking is infinite, essentially your theory does not have real supersymmetry. Supersymmetry is broken. So in this case, you have explicit, the limit gives you an explicit supersymmetry breaking. Gives you an explicit supersymmetry breaking in which the Goldstino is eaten up by the gravitino, because the mass of the gravitino is fixed. If you keep instead lambda SUSY fixed, so the scale of supersymmetry breaking fixed, then the mass of the gravitino, which is related, as I said, to the scale of supersymmetry breaking divided by the Planck mass. In the limit where the Planck mass goes to infinity, then this goes to 0. And in this case, you get a supersymmetric theory, and you get then spontaneous SUSY breaking. So you see, depending on how you do the limit to the rigid theory, how you go back, how you decouple gravity essentially, you can either obtain a supersymmetric theory where you still have supersymmetry breaking, because that's what we are looking at, which appears spontaneous supersymmetry breaking in your rigid theory as well. Sorry. Or you have explicit supersymmetry breaking, of course, with all the good features that you inherit from the fact that you started from a supersymmetry theory. And therefore, you have only soft masses, for instance. You don't have quadratic divergences, for instance, if you couple the MSSM to gravity. Okay? So the important thing, though, is that there isn't a unique limit. The way you take the limit to the rigid theory depends also on what are the assumptions you're making. Whether you want to keep the scale of supersymmetry breaking fixed, or you want to keep the gravitino in the spectrum with a fixed mass. Okay? So this is interesting because then you either get a real supersymmetric theory with spontaneous SUSY breaking, or something which has soft SUSY breaking masses. So it's not strictly a supersymmetric theory. Yeah.
In supergravity, supersymmetry are in the PhD, So, in general, I expect that in gauge theories, the only breaking that can have the gauge symmetry is spontaneous, because in general...
In supergravity, the supersymmetry breaking will be spontaneous. The point is that when you take the limit and you decouple gravity, then the breaking will be still spontaneous if you keep the scale of supersymmetry breaking fixed. If not, then I will show you explicitly an example. Don't remember anymore. Until when do I have now? 5:45, okay, yeah. So I should be able to show you an example where this happens explicitly, and the fact that you generate soft supersymmetry breaking terms. Okay? So in supergravity, the breaking is spontaneous. This is supergravity, you have supersymmetry, and then the vacuum breaks spontaneously supersymmetry, because you're finding yourself either here or here, I don't know. You take a minimum of your potential, you plug it in the supersymmetry transformation, and either these are 0 or not. If they are not, then you break supersymmetry. This is a spontaneous breaking, clearly. Though when you take the rigid limit, then this can become something different. The way you decouple gravity is subtle. That's, again, a point that I want to make. And this is particularly interesting when you have extended supergravities, because, again, when you have extended supergravities, as I told you, the extended supergravities will have scalar manifolds which are not necessarily Kähler. But in the rigid limit, you should always recover back Kähler manifold. So this means that the non-Kähler part should disappear when you take the rigid limit. And again, this has to be done in a careful way, because this happens, of course, if you do the limit in a way that allows you to have, again, spontaneous SUSY breaking also in the rigid limit. Otherwise, you have something completely different, and then the manifold does not need to be Kähler anymore, even in the rigid limit. That's the thing I was going to discuss now. Any other question on this? If not, I will discuss precisely that, the super Higgs mechanism. Okay, so as your colleague was just saying, if you have a spontaneous breaking, you should expect some sort of Higgs mechanism, and of course this is going to be a super Higgs mechanism. which I will discuss, of course, in the simplest of cases, because I want to give you the idea of how it works, not the general proof. It can be done with any cosmological constant, of course, and it can be done with any matter content. I will restrict myself to a very simple setup, which is the case of only chiral multiplets, so no vector multiplets, which means no d terms, okay? So my potential is only this one. And for what concerns the super Higgs mechanism, the thing that should happen is that the gravitino, which originally was a massless field, becomes massive. And it should incorporate additional degrees of freedom. Now, when you have the Higgs mechanism, you have a vector that eats up, you have a vector field, and this vector now essentially will couple to some scalar field in such a way that you have a new field, which is defined as this combination, which is massive now, and which, in addition to the plus and minus 1 polarization, carries also the scalar polarization. Now, the thing should happen exactly in the same way for the gravitino. You should have a gravitino that is the massive gravitino that should be a combination of the original one plus now what? The derivative of a fermion, though, not of a scalar. A fermion which is going to be the Goldstino. Is going to be the fermion that tells you the direction in which you break supersymmetry. And actually, since this is a spin 3/2 field, the correct way to do it is not just to, well, there are coefficients here. Now I'm being schematic again. Later I will show you the precise coefficient, but on top of this, you will also have a contribution of this type. And I will show you exactly why you need this kind of contribution momentarily. Okay? The thing, though, is that instead of defining the gravitino, the massive gravitino, so instead of taking the gravitino as it was before, you would like on your vacuum to have a gravitino which is massive, which contains the spin 3/2 polarizations which you had before, and which eats up some spinor that gives him the polarization plus and minus 1/2. That makes it massive. Now, how this works in practice, let me focus on the Lagrangian of the gravitino and the chiral fields. Okay, let me keep the conventions that I have here so that at least I have the correct numbers. So, well, I am in Minkowski, so this is really just a simple derivative eventually. Then I have the kinetic term, of course, here. And then I have the mass terms, okay? I have a mass for the chiral fields. And then I have a term, this is the interesting part, that mixes the gravitino with the chiral fields. And of course, again, plus Hermitian conjugate. Now, let me say what these are. Now, the mass, so first of all, let me recall the G Kähler potential, which is the combination of the original Kähler potential plus the logarithm of the superpotential square. Okay. And hence, when I define GI, I mean GI is simply the derivative of G. Okay? Now, S is precisely this thing here. This is S. Okay? It's the shift in the gravitino, and it's essentially the term whose square gives you this negative contribution in the scalar potential. And Mij, the mass matrix, is now, where do I have it? It's the second derivative, of course. Ah, here it is. Okay. It's the second derivative of the superpotential, and this is fine. But it can be expressed in terms of G, because this is going to be useful for later, in the following way. It's the second derivative of G plus the sum of the first derivatives. Now, in order to prove this, there are a few identities that one should work out. Let me spare you the details and just follow the structure, because that's the important message, okay? So, the thing is the following, essentially. If I look at the fermion part of the Lagrangian, because now I'm looking at the super Higgs, I want the gravitino to become massive, so I don't care about the rest. I look only at the fermions. I have the kinetic term for the gravitino and the chiralini, and then I have a few mass terms. The problem is that I have a real mass term for the chiralini here, a real mass term for the gravitino here, but I have also a mixture of gravitini and chiralini here. And of course, if I want to write down my theory in my Minkowski vacuum, so I'm assuming I am at a Minkowski vacuum, so by the way, the scalar potential in this language using the G rather than using G rather than the scalar potential, this can be written in the following fashion as well. Let me write this as well. This is MP square GI J bar capital GI capital JJ bar minus 3 M Planck to the 4. No, as I told you, as I already explained you, the superpotential essentially disappears. No, becomes a constant when you have when you introduce the scalar potential G. And the thing here is the following. So, in order to really understand what are the masses of the fields, I should somehow diagonalize my mass matrix. Here I have the problem that I have a mixture. And I have a mixture between a spin 3/2 and a spin 1/2. So what should I do here is I should redefine my gravitino exactly in the way that I told you before. I should redefine my gravitino in terms of the old gravitino plus some coefficient times this combination. This is the part that I want to remove. Chi I right, and then, yeah, well, if it's, yeah, well, okay, something like that. Okay? I want to remove the mixed term there, or better, probably if I want left, let me write left, and then this is the right part. Okay? I want to remove that term there, that mixed term, in such a way that I have the gravitino with its mass, and then the chiralini separated from the gravitini. Because one of the chiralini is going to be the Goldstino, which is going to be eaten up by the gravitino. Okay, the derivative part now is not important. That will have to do with the kinetic terms. I'm not interested in that. I'm not focusing on that now. I'm interested really in the mass, okay, to really show you the Higgs mechanism. Now, I'm doing this in Minkowski, for simplicity. So I'm assuming that V0, which means in terms of the G's that GI is 3, so that the potential is vanishing. And then in order to really check this, I also have to prove, well, I have to use the fact that I am at a critical point. No? I want to be at a critical point, I want to be in a vacuum, so I want to use the condition that I am at a vacuum and that I am in a Minkowski vacuum. Okay, so this is the condition for being Minkowski, and then I have a condition for being on the vacuum. And the condition for being on a vacuum, if I write it in terms of the G's, and how I have to take a derivative essentially of this potential, the condition is this one. And again, you just believe me. But you can check it by taking a derivative here of V. Okay? So these are the two conditions that I have to use in order to prove that I can decouple the gravitino from the chiralini, so that the Goldstino enters in the... So you see, supersymmetry breaking, so supersymmetry breaking means, in this case, that GI is non-zero on the vacuum, because GI is the derivative of G, which is essentially related to the derivative of the superpotential. No? If you write it in terms of this, you see that this is, you take a derivative of the Killer potential, plus I have a derivative of the log, so this is essentially a derivative of the superpotential divided by the superpotential. Okay, so you can rewrite this as the derivative of covariant derivative of the superpotential divided by the superpotential. And you see, in our case, we want this to be non-zero because we want to break supersymmetry, and at the same time we are in Minkowski, so W is different from 0, so I don't have any problems here. So I'm breaking supersymmetry. If I break supersymmetry, I should have a super Higgs effect. If I have a super Higgs effect, my gravitino should eat up the Goldstino. The Goldstino is this combination of the fermions. Why this combination? Because GI is telling you in which direction you're breaking supersymmetry. So clearly that's the combination of fermions that will give you the Goldstino. So this means essentially that if you take the final mass matrix should have a 0 eigenvalue, should have a Goldstino, a 0 eigenvalue in the direction given by GI. So now the procedure is pretty smooth. Essentially, you redefine psi in terms of psi hat, you plug it in there, and okay, let's try and let's do it. So if I write that with a minus, I still have, okay, so let me keep all the terms with two chi's. So let me look only at the terms with chi's, of course. So the new mass term for the Goldstini, for the chiralini is going to be the old mass term, plus I will have now a contribution from here, because from psi now I shift psi with a combination of the chiralini, and then I will have a contribution from here. Now each psi will contain a chiralino. So I will have a contribution from here, and this contribution will be proportional to 2s divided by mp square, of course, and then I will have the factor alpha there times now gamma mu. Yeah, there are some gammas. I should have better. Okay, let me write it with the fermions as well, so that we see that at work. Okay, so the first term is this. Then I have 2s over mp square, and then I have to do this redefinition. So psi is psi hat minus alpha gamma chi. Since this is a psi bar, this becomes a plus alpha gi chi bar I left gamma mu, and then I have a gamma mu chi j gj. This is this term here. I just essentially shifted from psi the term proportional to the Goldstino, and then I will have another contribution from the square, which is S over m Planck S over m Planck, and I have now an alpha square, and then I have g I again chi bar I gamma mu nu gamma nu chi j gj, and actually with a minus sign now, because one is I forgot the psi here. No, what am I writing down here? Gamma mu nu psi nu. Right. Okay, one is a psi and the other one is a psi bar. So one gets shifted with a minus and one with a plus. So this is the thing I get. And now you have to use gamma algebra. Gamma mu is a 4. Gamma mu nu, gamma nu gives you 12. You just check gamma matrix identities. There is not much there. Let me not enter into the details. And then you see that you have the same structure everywhere. You have the same structure everywhere because, I mean, here you have your mass matrix, and here you have two terms which are of the same type. They have Gi, Gj times the fermions, so I can forget the fermions, and I can define a new mass matrix, which is the old mass matrix, plus the shifts. Okay? So I have one term that comes with a 4 and the other that comes with a 12, and this becomes a minus S over MP. Yeah, there is an alpha, so S over MP, and I have 12 alpha square minus 8 alpha over MP GI GJ. Okay, so how do I determine the alpha? The alpha is determined very simply by the fact that after diagonalization, I don't want to have any more this term. So how do I get rid of that term? Well, simply from the square of the Gravitini here, because of the shift now, I get terms with one Gravitino and the Goldstino. I get 2 times, actually, Gravitino times Goldstino. And this contribution, Gravitino-Goldstino, should cancel exactly this one. So what you have is that from S, M Planck, what was it? M Planck, psi bar mu, gamma mu nu, psi nu, this spits out now 2 terms. If I do that redefinition, I get 2 terms with alpha, psi bar mu, gamma mu nu, gamma nu, chi g, and with a minus. And this should cancel this term here. Now this again is gamma algebra. This is just a 3 gamma. And so this tells you that alpha should be 1/3, and actually there is a mass Planck, so it's 1/3 mass Planck. So that everything now goes together, because now if you plug this into the mass matrix up there, you find that the new mass matrix is the old mass matrix And then here you start putting in your factors everywhere. And eventually you get that this is just S over MP cube, GI, GJ, with a factor of 4/3. I hope I got the factors right, but anyway, you can check it. And since Mij is also written in terms of GI, GJ in this way, you see that you get a new mass matrix which has the form of 2s over mp cube, the Planck mass square di gj, plus now a 1/3 gi gj. This is the final mass matrix you define. And you can now check that if you take Mij gj, this gives 0, because if you contract this with gj, the first term is the derivative of g times g, which, using the condition that you are on the critical point, is proportional to minus g. And here you get gi gj times gj, which, using the condition that you are in Minkowski, is 3 times the Planck mass. So when you do this, from the left you get minus m Planck squared g, and from the right you get plus m Planck squared g. So that is 0. So essentially what I'm telling you is, from now more in general, let's say that you have more fermions, also the Gaugini, you decide what is the Goldstino by looking at the coupling of the gravitino. The gravitino will couple in this fashion, no, with a psi slash, will couple to the Goldstino. So whatever you have that couples to psi slash is the Goldstino, and this is the mixed term between the gravitino and the other fermions. And this is the Goldstino which you have to remove from the spectrum, because it must be eaten up by the gravitino. So in order to do that, you redefine the gravitino in this way with the appropriate coefficient, and then you can check that the remaining mass matrix of your fermions doesn't have the Goldstino. The Goldstino is 0 mass, so you can forget about that. And essentially that fermion has become the fermion which appears in the gravitino, and that gives the extra polarization which are required in order to have a massive gravitino. Okay? Computations are a bit heavy, but the logic, I hope, is clear. Okay? If I have a spontaneous symmetry breaking, the gravitino should become massive, should eat the polarization that is missing, and this polarization must be provided by the other fermions. Which combination? Well, the combination is the one that appears in the mixed term between the spin 1/2 and the gravitino. You have the mass of the gravitino, the Lagrangian mass, you have the Lagrangian mass of the fermions, and you have this mixed term. Of course, on the vacuum, the mixed term better disappear. Should not be there. No, you should have that the gravitino has its own mass, and the spin 1/2 have their own mass. And they're separated fields, and they will propagate independently. So you have to remove this term. The way you remove this term is by shifting the gravitino, and after you do that, you can check what is the effective mass of the other fields and the mass of the gravitino. And the mass of the gravitino is related again, as I said before, to this S, which is nothing but the superpotential, essentially. Questions? Yes? Again, depends now. So the question is whether in anti-de Sitter the gravitino is still massive or not. So when you are in anti-de Sitter, as I said, what you call mass depends on the conventions. Now, there is a Lagrangian mass which appears also when you have supersymmetry. Because now I erased those equations, but if you go back to the anti-de Sitter case, so if you go back to the supersymmetry transformations, the supersymmetry transformation of the gravitino goes into the covariant derivative of the spinor, plus here there is essentially, let me be schematic again, the coefficient, well, probably I chose the coefficient such that that is exactly S. This is the transformation rule, and S is proportional to W. And as we said, in anti-de Sitter, S is non-zero because the potential is essentially minus 3S squared. So if you are in anti-de Sitter, this is non-zero, which means that the equation for the supersymmetry parameter that you have to satisfy is this. So epsilon will have a non-trivial coordinate dependence. You see, Minkowski, this becomes trivial. No, S is 0. This becomes the simple derivative, which means you can take supersymmetry parameters which are constant. In anti-de Sitter, now the space is curved. The supersymmetry parameters are not constant. But the other point is that S is going to be different from 0. So in anti-de Sitter, even in the supersymmetric case, this is non-zero. So this is non-trivial. But of course, if you are in the supersymmetric case, GI is going to be 0. Because GI is the source of supersymmetry breaking. No, I told you that GI is DIW divided by W. So if this is supersymmetric vacuum, then this better be 0. No, you can have spontaneous symmetry breaking, supersymmetry breaking also in anti-de Sitter. But if you're looking, I'm discussing the fact that in anti-de Sitter, you can have a Lagrangian mass for the gravitino, even if you are in a supersymmetric theory and the gravitino is essentially massless, because you would expect it to be massless essentially, no? Because it's in the same multiplet as the massless graviton. But then it depends what you call mass, as I said. There is a Lagrangian mass, but I don't know if I would call that mass. Okay, I would say that the gravitino is still massless. Yeah. Now, if you break supersymmetry, then on top of this, you will have this term, and then you will have to redefine things, and then you will have a gravitino which will have now a Lagrangian mass that is different from the value that preserves supersymmetry. So it's different from the value that you would need in order for the gravitino to be in the same multiplet with the graviton. From the point of view of counting of degrees of freedom, this is exactly what happens. If supersymmetry is preserved, this term is not there. So the gravitino is just the spin 3/2. If supersymmetry is broken, this term is non-zero. And then you have to redefine the gravitino in that way, and then you also have the additional spin 1/2. That's the point. The crucial, that's why I'm saying the crucial point is this one. It's the mixed term between the gravitino and the other fermions. Is that, if that is there on the vacuum, then you have to disentangle the two fields, and that is telling you where you're breaking supersymmetry. Okay? So I insist, the calculations here start to become maybe a bit more complicated, but I hope the concept is clear. When you break supersymmetry, the gravitino should get new additional degrees of freedom, and this come in a mechanism which is an analogous of the Higgs mechanism, only now it's super Higgs, and the Lagrangian mass of the gravitino should eat up the Goldstino, which is essentially the combination which couples to psi/slash. Any other question? Okay, I understand that we're already at the end of the afternoon, at the end of the third week. So you all start to be tired, but bear with me for 15 more minutes. I will maybe do some less calculations, but show you a couple of things which again are useful. and which have to do again with supersymmetry breaking. Now, when you are in a supergravity theory, as I said, the scale of supersymmetry breaking might be different from the cosmological constant. And generally, you would like, well, that depends on what you want to do now, but generically, people in phenomenology try to have a supersymmetric sector which is separated from a SUSY breaking sector for the reason essentially that you want to have that your supersymmetry breaking might happen at a scale maybe which is high and still allows you to have supersymmetric particles at an energy scale which is much lower than what you would naively get if you just look at the sector where you have supersymmetry breaking, because then you have some mechanism that transmits the supersymmetry breaking from what is called the visible sector, sorry, from the hidden sector to the visible sector. So somehow you assume these two sectors are separated, and then there is some mechanism that communicates the supersymmetry breaking from the hidden sector to the visible sector, and which has some way of suppressing the effects that come from supersymmetry breaking, which might be for various reasons, which might come from quantum effects. You have what is called anomaly mediation, or gauge effect. You have what is called gauge mediation. And for what interests us, you can have gravity mediation. So you might have two different sectors which don't talk to each other, or essentially do not interact. One sector maybe is your MSSM, and the other sector contains some supersymmetry breaking sector, which breaks supersymmetry, in such a way that the mediation is given by gravity. Now, since gravity, of course, contains the Planck mass, and all the interactions that come out in a supergravity theory are suppressed by the Planck mass, then this effect might be suppressed by the Planck mass. So this is a good way to somehow reduce the effect that you have on the visible sector coming from the supersymmetry breaking in a hidden sector. Now, one way to show this is by means of a very simple model, which is called the Polanyi model, which is an interesting model that was cooked up by Polanyi and was never published. It's in a proceeding, actually, or in a note that was never, in a preprint, actually, that has never been published. And the model is very simple. You take a Kähler potential, which is simply phi star, so one chiral multiplet, and take a superpotential which new mass scale m on top of the Planck mass, and then I have a combination here of my scalar field and a certain coefficient times again the Planck mass. I'm taking a renormalizable theory, so canonical Kähler potential, cubic superpotential, even though in this case it's not even cubic, it's linear in the fields, and then everything else is just a constant, with a certain coefficient alpha. Now, to write down the potential for such a theory is very easy. So in supergravity, the covariant derivative is the simple derivative. Well, in this case, I have only one field, phi. So I have to take the derivative with respect to phi of W plus the derivative of the Kähler potential divided by m Planck square times W. Now, the first is trivially m Planck. This just gives a phi star divided by m Planck square. So let me put, and then I have an m Planck here from the superpotential. So I get something like that. I hope I did things correctly. And then you have you can write down your potential. No? You know that the potential is e to the k over m Planck square, dw square minus 3w square divided by the Planck mass square. Okay, and I mean, you just take the square of these. You know, g phi star is canonical, so this is just a 1. So there is nothing here. This is really this object absolute value square. This is w absolute value square. And then what you do is you look for critical points. So you try and see whether you can solve d phi v equals 0. And you want, of course, to break supersymmetry. You want to find a vacuum, but you would like also to have a Minkowski vacuum. So again, this is the condition to have a vacuum. And this is the condition for having a Minkowski vacuum. Okay? And when you do that, you discover that you can do this for a particular choice of the parameter alpha. So alpha to be minus 2 plus root of 3, or you choose alpha to be 2 minus root of 3. In the first case, you solve these equations for phi, which is m Planck 1 minus root of 3, and in the other case, phi is m Planck root of 3 minus 1. Okay? Now, the scale of supersymmetry breaking, in this case, is given by dw. And if you plug in this value, you get that the scale of supersymmetry breaking is a number, which is not too important, is root of 3 times e to the 2 minus root of 3, whatever it is, it's a number, times the Planck mass, times this parameter that you introduce here. So this is a crucial parameter in my model, that small mass m. And that small mass m is nothing but the mass of the gravitino, because if I compute the mass of the gravitino, which comes from the superpotential, so this is related essentially to dw, and this is related essentially to w. The mass of the superpotential, the mass of the gravitino, sorry, is e to the 2 minus root of 3 times m. So small m is essentially the mass of the gravitino, up to a factor. Okay? So now, what happens if I take, so this is the Polanyi model, this is breaking supersymmetry. It's breaking supersymmetry at a scale, by the way, you see, which is a geometric average of the mass of the gravitino and the Planck mass. So you can choose, you can tune the scale of supersymmetry breaking, tuning the mass of the gravitino, and essentially how far it is from the Planck mass. And then, if you couple these to matter, in a very simple way, for instance, in this way, so you take a visible sector, so I'm taking the Higgs, the hidden sector to be the Polanyi model. For one of the two values of alpha that I mentioned before. And then I take a visible sector which contains a certain number of fields, again, canonical terms, with a superpotential, which is a function of these fields. Let's say that these are, for instance, the fields of the supersymmetric extension of the standard model. Then what happens if I write down the potential? The potential, the full potential now has the following structure. The full potential is e to the k h plus kv, of course. And then what do I have? You see, since I'm assuming that the kinetic terms are all canonicals, I can split essentially the part where I have the derivative with respect to phi of my superpotential, and then the derivative with respect to the other moduli, the yi's of the superpotential. And here I have w hidden and w visible. And now here comes the interesting point, no? That since I assumed that the superpotentials are also split, d phi w is essentially the d phi of wh, which I had before, plus I still have a term proportional to phi star, which comes from the derivative of the Kähler potential times W visible. Okay, so I don't have exactly the same derivative that I have here. I have an additional piece. And if I look at the derivative dIw, I clearly have di of W visible plus I now have an additional term, again, m Planck square W hidden here. So now what is the point? The point is the following. If I assume that my alpha has been chosen like in the Polanyi model, you see I can essentially from here extract the contribution that comes from the first term and cancel it with the contribution that comes from here. Because in the Polanyi model, these are canceling each other. And then I have to rewrite the rest in various pieces, which, though now will depend on the background value for the field phi. So essentially, I'm stabilizing the field phi in the Polanyi model, as in the Polanyi model, in such a way that the two terms will cancel with each other. And then, essentially, my expansion, here I have that e to the kh is a number, so let me forget the numbers. I have the visible sector, and then I have the various pieces that appear. So the square of this is cancelled because it's in the Polanyi model. This now, phi, remember, has a specific value in the Polanyi model, no? So this is a number, essentially, which multiplies W. So I end up having a contribution, a certain number, and phi, yeah, let me rewrite phi, what was it? I said before that phi is essentially the Planck mass 1 minus root of 3 or root of 3 minus 1. So essentially from this I get something which goes with W divided by the Planck mass. So the remaining term is something like W visible squared divided by Planck mass squared from the first piece. From the second piece, I will have the derivative of the visible part squared. This is the globally supersymmetric term, essentially. Plus, I will have now W hidden, which, as I said before, is essentially the mass of the gravitino, times the Planck mass square. So we'll end up having, so this term here becomes yi star times the mass m. Because on the vacuum, up to a coefficient, on the vacuum, W hidden is essentially small m. That's what we saw, small m times m Planck square. We said phi goes like m Planck, so this is small m times m Planck square. So this means that here you get just something proportional to small m. So this means that out of those terms, you see, you start getting terms like y square times m square, which are finite, plus again terms which are suppressed in the Planck mass. Now let me forget all the terms which are suppressed in the Planck mass. And the same is going to be true for the last part. The important thing is precisely this. You see, this would be the supersymmetric thing. When you send m Planck to infinity, this goes to 1. This is the MSSM, the standard MSSM, let's say, this MSSM potential. This is going to be suppressed when m Planck goes to infinity. Everything else is going to be suppressed. But now you generate terms which in the limit m Planck that goes to infinity are not suppressed. And these are indeed masses, mass terms for your fields, which are essentially soft supersymmetry breaking terms. So you see, I took a small m, which is the mass of the gravitino, and I'm doing now a limit where the Planck mass goes to infinity, but I keep m finite. And if I do that, then you see I don't get the MSSM, but I get the MSSM with soft supersymmetry breaking terms. And now this is to say that essentially, if you take the MSSM and you introduce soft supersymmetry breaking terms, you can think, not always, but you can think that in some instances, these soft supersymmetry breaking masses are coming from the fact that you broke supersymmetry in a supergravity theory, in a hidden sector, and then the fact that you don't see perfectly a supersymmetric theory, but you have some explicit supersymmetry breaking, is nothing but the residue of the limit in which you decouple gravity. So you broke supersymmetry in a theory spontaneously, in a theory with gravity, but when you decouple gravity, you're left with a theory which is not supersymmetric, but has some soft supersymmetry breaking masses. Okay? And then there is one more type of models that I'm interested in showing you, but I will show you tomorrow, which are the no-scale models, because they are ubiquitous in string theory. They appear in all string theory compactifications, and therefore there's a lot of physics that comes out of that. But this is, again, to go back to the previous statement. So what I showed you today was that when you break supersymmetry, first of all, in supergravity, you can break supersymmetry with zero or negative cosmological constant, not just with a positive cosmological constant. That the scale of supersymmetry breaking and the cosmological constant are related by means of the mass of the gravitino, by the value of the mass of the gravitino, but essentially then you can tune them separately. And then that when you go back to global supersymmetry, you might get a theory where you have still spontaneous supersymmetry breaking if you keep the scale of supersymmetry breaking finite and you then discover that the gravitino essentially goes to zero mass, and that's the reason why you get a Goldstino still in your theory. Or you can have a theory where supersymmetry is explicitly broken but by soft masses. And this is exactly what happens in this model. You have that supersymmetry is broken explicitly but with soft masses, because the scale of supersymmetry breaking here, of course, is very high. We saw it's an average of the mass of the gravitino and the Planck mass. And in the limit where you send the Planck mass to infinity, then essentially this scale goes to infinity while you keep the mass of the gravitino finite. This means that the final theory is not supersymmetric with supersymmetry breaking, but it is a supersymmetric theory with the addition of some explicit terms which break supersymmetry, but which, however, of course, have a good behavior of divergences because it comes originally from a supersymmetric theory. So you're introducing explicit supersymmetry breaking terms, but these have the origin from a supersymmetric theory, and therefore they break supersymmetry nicely. That's the idea. Okay. I guess there are no questions at this point. Enjoy the dinner. I'll see you tomorrow. And then we'll move on to